Can a machine learn, reason, and solve problems in ways that seem intelligent? Artificial intelligence sits at that question, linking computer science with tasks such as perception and language understanding. You will move from basic definitions to major approaches, benchmarks, debates, achievements, limitations, ethics, and future challenges. Artificial intelligence is a branch of computer science focused on creating systems that can perform tasks that usually require human intelligence. These tasks include learning, reasoning, problem-solving, perception, and language understanding. In this unit, AI is presented as the simulation of human intelligence by machines designed to think, reason, and learn. The historical development of AI begins with important early ideas about machine intelligence. In the 1950s, Alan Turing introduced the Turing test. In 1956, the Dartmouth Conference established AI as a field. And in the 1980s, expert systems gained prominence. Several milestones show how AI evolved into a practical field. In 1997, IBM Deep Blue defeated world chess champion Garry Kasparov. In 2011, IBM Watson won Jeopardy! And in 2017, AlphaGo defeated a Go champion. Modern AI often relies on data-driven approaches. These models use large datasets for training, so they can identify patterns and make decisions. The content highlights applications in computer vision, natural language processing, and robotics, including image recognition, language translation, chatbots, and adaptive learning for task automation. The material distinguishes between narrow AI, general AI, and superintelligent AI. Narrow AI is designed for specific tasks, with examples such as virtual assistants and recommendation systems. General AI can perform any intellectual task a human can do and remains theoretical, while superintelligent AI is described as a hypothetical future form that surpasses human intelligence across fields. AI systems depend on several core components. Data provides the foundation for training and decision-making. Algorithms supply the rules and processes for solving problems, models represent real-world systems, and computing power supports large datasets and complex models. One major approach is symbolic AI, sometimes called good old-fashioned AI. It uses symbolic representation, logical reasoning, rules, and knowledge bases to solve problems. The material also describes knowledge-based AI as relying on explicitly programmed knowledge, with examples such as diagnostic systems in medicine and expert systems like Mikan. Machine learning enables systems to learn from data without explicit programming. The key methods named here are supervised learning with labeled data, unsupervised learning for patterns in unlabeled data, and reinforcement learning through trial and error. Examples include image recognition and spam filters. Deep learning is presented as a subset of machine learning that uses neural networks with multiple layers. The summary table describes input, hidden, and output layers, while activation functions introduce non-linearity. Applications named in the material include image recognition, natural language processing, autonomous vehicles, and voice recognition systems. Natural language processing focuses on interaction between computers and human language, with applications such as language translation and chatbots. Evolutionary algorithms draw inspiration from biological evolution, including natural selection and genetic algorithms, and are used for optimization problems in logistics. Hybrid AI combines symbolic AI with machine learning to use the strengths of both. 0203 0405. Modern benchmarks offer a more nuanced and comprehensive way to measure performance across domains. They focus on precision, scalability, and applicability in real-world problems. The Turing test is limited in three main ways here: It is human-centric because it measures imitation of human intelligence rather than excellence in specific tasks. It also lacks task-specific assessment and can be vulnerable to deception through conversational tricks without true understanding. Several benchmarks illustrate how evaluation has changed. Glue and Superglue measure natural language understanding across tasks such as sentiment analysis, question answering, and text entailment, and the material links them to progress in models like GPT and BERT. ImageNet benchmarks object recognition and classification, while COCO evaluates detection, segmentation, and captioning in complex scenes. Other benchmarks focus on learning through interaction and action. Atari and DeepMind Lab test strategy, learning in environments, and OpenAI Gym provides standardized environments for reinforcement learning tasks. Squad measures machine reading comprehension, while robotics benchmarks such as RoboCup assess navigation, manipulation, and interaction. The Church-Turing thesis is described as foundational but limited for modern AI development. It assumes abstract computation with unlimited time and memory, which does not fit real-world constraints. The material also says it falls short for dynamic learning, continuous processing, nonlinear transformations, interaction with environments, and ethical or context-sensitive decisions. 02030405. The philosophical discussion compares machine intelligence with human intelligence and asks what understanding really means. The Turing test emphasizes functional imitation in conversation, while critics say it rewards imitation more than understanding. Searle Chinese Room argues that a machine can manipulate symbols without understanding their meaning, and the system's reply answers that the whole system could still exhibit understanding. The achievements listed here show AI succeeding in both competition and daily use. Deep Blue in chess and AlphaGo in Go demonstrated advances in strategic reasoning. The material also names autonomous vehicles, speech recognition in virtual assistants, and recommendation systems used by Netflix, Amazon, and Spotify. The same material stresses that AI still has important shortcomings. Narrow AI performs well in specific tasks, but lacks versatility across domains, while general AI remains theoretical. AI systems can also struggle with unexpected scenarios, and biased data can produce flawed decisions that affect fairness and accuracy. Ethical AI in this unit centers on bias, fairness, transparency, privacy, and accountability. Biased training data can affect areas such as hiring, lending, and law enforcement. The material also notes that many deep learning systems act like black boxes. So, explainable AI aims to make decisions more understandable and trustworthy. AI is shown transforming healthcare, finance, retail, transportation, manufacturing, public safety, and education. Examples include diagnosis systems, fraud detection, personalized shopping, self-driving cars, predictive maintenance, and personalized learning. Future challenges include job displacement and reskilling, privacy concerns, misuse through cyber attacks or misinformation, autonomous weapons, and the need for international collaboration and regulation. That balance is central to building AI systems that are effective, reliable, and responsible.